So let's just look into the principle of finite element analysis into a more concrete language. Okay. So as you can see here, the finite element analysis is a computational technique for obtaining approximate solutions of boundary value problems in engineering. What does that mean? This slide is very abstract, okay? If you think about your differential equations, right? You learned that in your first year mathematics. So what does differential equations tell you? Typically, you have a differential equations that work, for example, if it's one-dimensional, it works on the whole x-axis, right? R, right? It's not bounded. So you have a differential equations and you try to solve it, you get back some other function, right? This is how differential equations work. But in real engineering, everything has a boundary, right? For example, you have a square plate, right? Imagine you have a square plate and you start to, for example, heat it up at one corner, right? And the heat is going to redistribute throughout the whole plate, right? Imagine the heat is not going to go away from the plate, then the heat will be redistributing inside the whole plate, right? And how this heat will be moving inside this plate, right, is governed by a differential equations, but you are not solving this differential equation in the infinite two-dimensional space, right? You are confining the heat into a square plate. So that's the boundary value confined when you try to solve the heat distribution equations in the plate, right? That's the boundary value or the boundary conditions imposed on your differential equations for heat conduction, right? Because this boundary is generally irregular, as we see in the previous lecture, FEA is a way to help you break down this boundary of irregular shape, right? So this is what you mean by the first sentence. It's basically solving a differential equations with a boundary conditions that you cannot analytically handle, right? Once you solve this boundary value problems, right, it's also called field problems, right? Because you are confined into a field, right? Think about a football field in the whole of Sydney is confined into a small area of Sydney. It's a field, right? And that field, right, is basically a physical structures in most of the cases inside your engineering problem. Now the field variables, right, are the dependent variable of interest governed by the differential equations. Now what does that mean? So what's the field variable that we are typically want to solve in FEA? Well, if you go back to previous slides, you can see that the displacement where I put the structure under external loading will be the field variables that we are interested in. The displacement is dependent on, first, how much the force is applied to the structure, and secondly, what's the mechanical property, the K value of the structures. So those are my field variables that I try to solve using FEA, right? And the boundary values, right, specified what's the conditions to fulfill the boundary. For example, the force goes to, for example, the displacement goes to zero if the boundary is fixed at a certain point, you're not allowed to move, or at a specific point, I know exactly where the force are, I know I applied that much force at that point. So those are the boundary values. Now you know from the differential equation courses that if you solve the differential equations with the boundary value given, then the solutions of your differential equations will be unique, right? If you solve a general differential equations, you always have some constant at the end, right? That give you a family of equations. But if you give a specific boundary value, you are fixed to a specific equations for the problem you are given. And this is exactly what happened in finite element analysis. If we put this into more mathematical formality, or put this into a mathematical languages, then these things looks roughly like something like this. So imagine you have a shape, a two-dimensional disk, for example, right? So for anything two-dimensional will be described by two coordinates x and y, right? So the field variable in general is something continuous within this boundary in two-dimensional space. So let's just call it phi. Phi is a function of x and y, right? Is the function of the position of the point in this coordinate system. Okay, this phi could be like displacement, could be forces, could be the heat distribution, could be many other things. Let's call it phi, keep it general, right? You don't need to, if you're struggling what this really is, this is just basically a continuous function, right? Phi, x or y. Now, this phi value, how do we determine it? Is basically determined by some underlying physical equations, right? So there are some underlying physical equations tell you how to get to this phi xy, and let's call that E, right? So that the phi satisfies equation of E phi equal to 0, right? You don't know what that means. You can think about, say f equal to minus kx in the Hooke's law, then f minus kx equal to 0, so f minus kx is this equation on the left hand side. It establishes some function of x in this case, which is f minus kx, so that gives 0, right? Now you know that this phi is of a very irregular shape. Is a ellipsoidal shape in this case. Okay, it's a bit difficult word, but it's irregular. Okay, so we want to instead of solving these equations strictly, right, solve these things, we break it down into determine the value at every point p, xi, yi. So you put a lot of points inside this shape, right? Hopefully evenly distributed inside the shape. Now, if I can work out at this individual point what are the corresponding equations, right, then the whole thing will still satisfy. That means if you sum up all these equations for all these points, they build up, you somehow give back to these continuous equations, then it made your life easier. You just made to solve all these individual points and then put it all back together, and you will be able to understand how the whole thing works when you have something applied to it externally. Now, just a few notes, okay, two important notes. Now, finite elements in most of the cases is not a differential element. In the two-dimensional case, it's not really dx by dy or dx times this dy. I use a lot of analogy of differential calculus to explain this whole thing work, but as we'll see later, this is not really a differential element because you also need to consider the mechanical property, the material property inside your whole structure, right? And a node is a specific point in the finite element at which the field value is to be explicitly calculated, right? Just go back to our previous slide where you have all these elements and all the nodes. Now, what this last sentence is saying is that we will be only interested in calculating the field variables at those nodal points, right? That's two important things you want to understand behind the principle of FEA.